everyone, let me introduce you to Eli Boling. Eli is a member of the C++ R&D team and has been working on these tools for a long time. I've known Eli for a long time. But Eli, I'll turn it over to you, and maybe you want to give people a little background. And I know over the years you've been blogging about all sorts of low-level, internal, interesting stuff as we've moved on to the multi-device world in particular, but then this session on C++ exception handling. And I'll turn it over to you, Eli.
Hello, good morning, good evening, whichever it is for you. I've been, as David said, working on the C++ tools for a long time. I've been working on the linkers, on parts of the debuggers, the compilers, the runtime libraries for as long as I can remember. And I usually am down at the low level of saying things. Today I'm going to go over C++ exception handling, which is an area that I've spent a lot of time in over the years. From the perspective of what we had to do to support it in the multi-device world. Not so much a little bit of the language feature itself, a few little details there, but a little bit more about, a lot more about the details of the underpinnings of the support on the different platforms. And maybe some of the implications to you, a few implications in terms of performance, and some of the possible future feature implementations, implications. So, next slide. So, I'm going to give a very brief review of some of the syntax for C++ exception handling. So the standard C++ exception handling syntax is try and catch. There were some extensions in the Win32 land for try, except, finally, and we're not going to be supporting try and except so much in the mobile spaces. I'll go over that a little bit more later on. But when try and catch, you have a try block followed by a catch block, and the try block is protected, and if an exception is thrown that matches the catch handler specification, the catch block is executed. And then catch handlers can be like the first one, where you catch anything, and then all exceptions are caught by the catch block, or they can be specific to a particular type. And there are multiple ways in C++ of catching the exception objects. You can catch them by reference, you can catch them by value, you can catch them by pointer, and there are different points of view about which one's best or most appropriate. I'm not really going to go into those very much. The types of the catch handlers matter a fair amount when you're talking about the way we interact with Delphi exceptions. And then if you are within your catch block and you decide you want to reissue the exception, throw it further up, and keep kicking the can down the road, you can rethrow the existing exception with a simple throw statement. I'll touch briefly on exception specifications because they're gone, and I'm really happy they're gone. They were a flawed concept in C++. I don't know if anybody of you folks are actually using them, but if you are, stop. They're not good. This is where you take a function declaration and you include in the declaration the description of the exceptions it might throw. And the problem with exception, there are many problems with exception specifications. John Spicer has written about them as a shadow type system. Herb Sutter wrote a long write-up on them as why they really don't serve to help you very much. Part of the problem is they're optional, and or they were optional, and as a result you could never know for sure whether or not a particular function was going to throw an exception of a particular type or not. So you might participate and say that you were only going to throw a particular type of exception out of your function, but if you called some other function which could throw some random exception that you didn't know about, your promise about what exception you might throw is is neither here nor there, and the effect is that your app will just get taken down. So it's really a very unfriendly feature, and in C++11 it's been deprecated. You can use no except. No except just is it's pretty mild thing. It just tells the compiler that the particular function is not going to throw an exception, and that may allow the compiler to do some optimizations, although I'll touch on that a little bit later when we talk about hardware exceptions. Next slide. So I'm going to get a little bit into the details of cleanup semantics here. In C++, objects, if you're with declare local objects inside a function, and those objects have destructors, then they have to be cleaned up in the event of an exception. And so I'm going to give a couple of examples where some of the more esoteric examples. So if you have a class, and here I have class X that's derived from some public base, and it has a member which provides a value. And let's say that the class is fairly complex. It has a destructor. It has to do some sort of cleanup, maybe to deallocate some memory when it gets deleted, otherwise you leak memory. And then you have a function f, which is a factory for these things and produces x's. And then I've just declared this silly little function which takes a bunch of integers, mathy function. So, and in the first example where I call mathy function with a string of, you know, oops, there's typos in there. No, there's not. With a string of calls to f, 3 different calls to f, each of those creates a temporary. And the rules for C++ are that those temporaries hang around until the end of the statement. So the end of the semicolon, once the function call mathy function returns, those 3 temporaries have to be destroyed. And so if an exception is thrown by, so when you're creating the parameters for mathy function, the first call to f will allocate an instance of x, or construct an instance of the x class, and then it'll call the value function on that instance. Same for the second, same for the third. If an exception is thrown anywhere in there for any of those 3 values or for any of the constructors, then the ones that have already been constructed have to be destroyed, and only the ones that have been constructed. So the semantics are actually quite specific and quite detailed, and underneath the covers there's a lot going on inside this simple call to mathy function in terms of doing the bookkeeping on what object has been constructed and what object hasn't. And in the event of an exception being thrown out of one of these calls, the right things have to be cleaned up. Same thing holds true for the question mark colon operation below. A temporary is created for the first call to f, and then based on the result of that, you either call do something with a call to f, which actually results in another temporary, or you call the function do something else. And in the second case, you don't create the second temporary. And in any case, whichever temporaries got created, conditional or not, they have to be destroyed at the end of that statement. Or if an exception is thrown in the middle of that statement, either by do something or by do something else, only the temporaries that have actually been constructed have to be destroyed. So again, some fairly complicated bookkeeping. And the reason I'm mentioning this now is it's related to hardware exception handling, which I'll come back to a little bit later on. Okay, next slide. Exceptions in the Delphi RTL. So in particular on multi-platform, we're not generally talking about just pure C++ apps. We're talking about hybrid applications that are using the Pascal component libraries, VCL, FMX, and also inherently the Pascal RTL. And that comes with an entire set of exceptions, an exception class hierarchy. that can be caught in C++. And there are some different semantics for the way C++ and Pascal exceptions are cleaned up and in how they're thrown. So we have a bunch of support in our runtime libraries to differentiate between the two and to make sure that the two interoperate properly. There are, in particular, some differences in the way exceptions are handled if an exception happens during the constructor of a class. So there's different rules between C++ and Pascal. In Pascal, all the base class destructors are called regardless of whether or not the entire hierarchy was constructed, and in C++, only the base class destructors are called for those base classes that were fully constructed. And that's specific to the case where an exception is thrown out of the constructor in a class. C++ exceptions can be caught in Pascal if they're the proper type. And by this I mean if the class that the type of the exception that you're throwing has to be derived from a Delphi class object. So any object that's been declared with DeclSpec Delphi class. I should have said that in C++ you can actually catch things like regular old integers and any type, whereas in Pascal you're restricted to catching exceptions that are derived from the T-object type. You can't catch a regular old integer in Pascal. The Pascal RTL supports hardware exceptions, and I'm going to get into a lot more later. But this is the mechanism by which we generally support intercepting hardware exceptions in C++. On Win32, we supported it as well with try except underbar try and underbar except. But we're not really supporting those on the mobile platform, so we don't really have plans for it in the future. That might change if there is a really sufficient demand for it, but I don't think it's really necessary. So in the Pascal RTL, when depending on different platforms, we install handlers which watch for the hardware exceptions, and they convert them, or they essentially reissue them as in the form of a regular old language exception, but bound up inside of wrapped up inside of a Pascal RTL class that's derived from T-exception, and they have a bunch of different subclasses to describe the various different hardware exceptions. They might be access violations, they used to be stack faults, I'll talk about that later too, and floating point violations. The most common ones are the floating point violations and the access violations. Next slide. Okay, so exception handling in a multi-device world. For the longest time, we were dealing with Win32 only. And now we have a whole bunch of different platforms to deal with. We have multiple processor architectures to deal with, x86 and ARM. There are 32-bit and 64-bit versions of both of those architectures. And we're dealing with OS X, iOS, Android, and Windows operating systems. And I discriminate between OS X and iOS because although they are the same basic code base and the same basic APIs, there are in fact some pretty significant differences between them with respect to, obviously how your applications are built, and certainly with respect to how exceptions are handled. It's they're markedly different. So dispatching and handling of language exceptions isn't really standard. first of all, there are, on some of these platforms, there are built-in systems for the process of dispatching exceptions, and some of these are built right into the operating system, well, specifically in Windows. But in most of the platforms, there is no operating system specific method for dispatching exceptions. The common platform, if you will, for dispatching exceptions on most of these platforms really comes from the Objective-C or the C++ compilers and the runtime libraries that come along with them. And some time ago, there was an effort right around the time the Itanium processors came out to build a C++ ABI. So this was an application binary interface which described all of the details of C++ interoperability. And that included type information layout, class member layout, class vtable layout, name mangling, RTL helper functions, what you do when you're creating vectors of objects, how constructors are called, how many different types of constructors there are, how copy constructors are named and how they're called, everything. So that the point of this was to arrange it so that if everybody wrote to this standard, then different compiler vendors could have their compilers generate code that would be compatible with each other. So a lot of you are probably familiar with the fact that the Embarcadero compilers on Windows pretty much forever have not been compatible with Microsoft, and that's because Microsoft had their own ABI and they didn't publish it, and we had our own ABI from way back when, and for a while we were the leader on the ABI, and they just differed, and there was no way that they were ever going to match up. And meantime, on Linux, there was an ABI that was being developed by GCC, which was just a de facto ABI over there. So anyway, this ABI was built up out of a consortium. The new ABI was built out of a consortium of people right around the time Itanium was coming out. And it included a very detailed description of how exceptions would be dispatched, how they would be unwound, how the stack unwind process would go, so that when you throw an exception, the exception has to travel up the various different stack frames to ultimately where it's going to be caught. And some of the stack frames in between the point where it's thrown and where it's going to be caught have to be cleaned up. Some can just be tossed. And when I say cleaned up, you have to go through and delete C++ objects that were created locally, even if the frame doesn't actually want to catch the exception. It still needs to clean up those locals to make sure there's no memory leaks. And this standard for dispatching exceptions for C++ included provisions for supporting other languages. And it was geared towards C++, but it was also geared towards these other languages so that you could plug in your own exception objects. It didn't require specific knowledge of the C++ RTL or the C++ class layouts to deal with the exception handling system. It was a little bit agnostic in those respects. And it was pretty nice, and we actually used it. We modeled our exception handling systems after it in the years between. Thank you. And other vendors started taking this up. As I said, this was a consortium. It included Intel and Microsoft and GCC, the people doing GCC, and the full ABI, the C++ ABI, was supported ultimately by GCC, and is supported by Clang. The exception handling API was also supported by those platforms. But and I should say it also showed up in the Win64 world, sort of. Elements of it show up in the way they do stack unwinding in Win64. But it was not adopted in a totally consistent manner. So it's a little unfortunate because the unwind system was really kind of platform agnostic. There were a few places where it actually touched the platform and had to deal with things like the processor registers, but there are very few. And it really had great promise for, maybe supporting the notion that you have to implement your exception handling system once and be done with it. And I think the GCC people really thought that they had it made in that respect, because they implemented a PC-mapped exception handling scheme where they used dwarf unwind information, which was platform agnostic, and so they didn't have to deal with too many of the processor specifics at on every platform they went to. And the underlying runtime library could just be the same. Well, when we got into the world of the mobile devices, it turned out to just not entirely hang together. Next slide. I'm going to go over the various different platforms right now. Win32, Win64, OS X, iOS, and Android, and describe briefly some of the differences between the platforms for support of our supportive exceptions. So Win32 is the old standard. The operating system defines the unwind system. Different languages all participate in the same system. It is easy for languages to participate. It is a non-zero cost method. So within the exception handling implementations, there are really two basic kinds. One is the non-zero cost method, where any function that wants to catch an exception has to make essentially API calls to say that the function is interested in exceptions, has to install a handler. Set jump implementations are like this, and the Windows system is like this too. It's just very much more efficient. You can generate the code inline to install handlers for a particular method. It's still non-zero cost, so that means that in the event an exception is not thrown, there's still some overhead in a function. With a PC map system, there's no overhead for throwing exceptions. What happens in the PC map scheme is the compiler and the linker collaborate to generate a very detailed map of the address space of the application. And so when an exception is thrown, the runtime library takes the instruction pointer at the location the exception is thrown, and it goes and looks up that inside this very detailed PC map, and then determines, based on the information in the map, what has to be done, which function it was in, and what has to be done to unwind the stack frame for that function. And once you've unwound that stack frame, you know where the previous stack frame was, and you know where the previous location was in the code, that stack frame, and then you continue that process. So it imposes no cost on the application when it's running if there's no exceptions. Imposes a slightly higher cost when an exception is thrown, but that's generally perceived to be the best balance of choices for performance for people. The exceptions are the unusual case. You don't normally throw exceptions at a high rate of speed in applications. They are the exceptional case. So Win32, it's a non-zero cost method, but it's fairly cheap. The unwind process is very coarse-grained. In Win32, the unwind system did not make any real built-in specifications for, as it unwound stack frames, how you would restore things like call saved registers. So in Win32 on x86, when you call a function, the function has to preserve typically a certain set of registers: ESI, EDI, EBX, EBP, ESP, and when you return from that function, those are expected to be restored to the same values that you had going into them. If an exception is thrown, the same thing is generally, supposed to be true, but the operating system did not define how that was going to happen. So it became up to the implementers of the language to deal with that problem. And everybody had to kind of trust each other that they would, in fact, restore these registers as they were, unwinding stack frames. And so let's see. Hardware exceptions are integrated into the same system. So the operating system defined a method for installing handlers, and it defined a method for issuing exceptions, so that they would start the unwind process, and the operating system included the the basic unwinder that would go back and call back into the language's handlers as it was unwinding the stack frame. If you got a hardware violation, like an access violation, an invalid instruction, a floating point operation failure, those exceptions would be propagated up the exact same system, which was nice, because then you didn't have two parallel systems and you didn't have to work so hard to integrate them if you wanted to. And on most of the other platforms that we deal with, we do have to do quite a bit of work to integrate the hardware violations with the exception handling system. On Win32, the structured exception handling concepts, namely underbar try and underbar accept, showed up. And these were fairly specific to Win32 and to the x86 architectures. They are, potentially, they can be moved to other platforms, but the advantages of doing that are they're pretty limited. Most of the times for try and accept, they were used for catastrophic application failures in C code. Sometimes they were used for implementing your own on-demand allocators. So you could, for example, and you sometimes could create blocks of memory that were reserved, and then when you got an exception touching one of the pages, you could commit some of the pages, and we used to do that for some of our systems. But it's a little bit outmoded, and I don't think we're going to really be wanting that on the mobile platform. So right now we don't really have any plans on carrying those forward. Next slide. Win64. So again, the operating system defines the unwind system, and different languages all participate in the same system. It's a zero-cost method. It's a PC map system, so you don't have to install handlers in functions as you enter them. The compilers have to generate a platform-defined unwind info. Yeah, the unwind info is actually defined by Microsoft, and it's very detailed. It's very fine-grained. It provides for very faithful stack unwinding with call saved registers being restored properly. It provides for extremely faithful stack traces, so that you can use the unwind information from any point and get a very, very accurate stack trace through any function that participates. And you really have to participate in it, because if you try to unwind past a stack frame which does not have this information, the operating system will kill you. And the nice thing about it is it's fully defined by the platform, so there's no argument about who owns it. So it's not provided by, it's not something that's part of the GCC family of compilers. It's provided by the platform. Downside, it's a bear for assembly language. That's kind of true of a lot of the other platforms. But this is the first time. And Win32 is easy for assembly language to participate in exception handling, and Win64 is kind of a pain. Again, hardware violations are integrated in the same system. If you get an access violation or floating point violation, it's propagated through the unwinder in the exact same way as language exceptions are propagated. Which is convenient. And again, structured exception handling constructs appear on that platform and are supported on that platform. This platform is also a little unusual, different from other platforms, and it allows you to add in dynamically to the PC map. So at runtime, if you want to allocate code, you can actually allocate new PC map entries so that they can participate in exception handling as well, and that's pretty unique to all the different platforms we're talking about. Next slide. OS 10. So on OS 10, the unwinding system is vendor specific. The operating system provides no defined exception handling system. The quote-unquote standard on that platform would come through GCC and or Clang or Objective-C, but it's all part of the GCC tool chain and the runtime library. When we targeted that platform, we did it through BCC32. And BCC32 does not use the same ABI and could not share in the C++ libraries from the platform, and we really could not use their unwinder support. So we used the work that we did way back in Kylix. For those of you who are that old and actually remember it, that was when we did our Linux toolchain. It was a PC map scheme. It was Intel 32-bit specific. Very compact, very fast. And we just retrofitted that to use with BCC32. It is a no-cost system for when you're executing code. You don't carry any burden. And when you throw exceptions, there's a little bit more of a burden. We supported hardware exceptions on OS 10, but those are not handled through, since there's no operating specific unwind system, you have to support it through whatever, you have to build your own. So on OS 10, if you want to catch access violations, you have to do it through mock APIs, MACH, which are part of the low-level mock kernel, which is the underpinnings of the operating system's kernel. And on OS 10, actually on OS 10 and iOS 32-bit, that requires that you spin up an additional thread to watch for exceptions. So when we catch hardware exceptions, you're always having at least two threads, one for the main app and one for the thread that watches for exceptions. We support handling access violations, invalid instructions, and floating point exceptions. We don't support underbar try and underbar accept on those platforms. I know the compiler actually let those go through, but we're going to be changing that so that it generates an error. I don't think there's sufficient demand on it, but we'll take feedback on that. And as I said before, we don't support mixing C++ libraries from the platform because we built this platform off of BCC32, which was not ABI compatible with the default compiler on that platform. So we don't have to handle the issues of exception handling interoperating between the different libraries, the C++ libraries. Next slide. iOS 32-bit. Okay, so for iOS, for C++, it's an ARM-based platform, and we ended up using the Clang compiler to target that platform. The Clang compiler, there are various different reasons for doing that, but the Clang compiler for this platform is, of course, ABI compliant with, compatible with the C++ RTL and compilers that are normally used for that platform. This is the Clang compiler that we build. So that meant on that platform we could actually use the C++ RTL on that platform, and we could participate in the unwind system that is part of the C++ RTL on that platform. That was that was relatively useful. Now, again, on that platform, the unwind system is defined by the C++ compiler and the C++ RTL, and not by the operating system itself. So the odd thing about that platform is, and this is a little bit of a surprise to us, is rather than it being a PC map scheme, it was a set jump long jump based implementation. So in many respects similar to the Win32 implementation, a little bit different. And that set jump long jump implementation was it basically used the C++ ABI for exception handling, but it had to modify it somewhat in order to make it work with it. So this is where I'm talking about inconsistencies between the different platforms in using that, generic C++ ABI for exception handling that was defined years ago. The set jump long jump implementation, I'm not sure why Apple chose it. It may have been concerns about space, because it is actually smaller to implement a set jump long jump implementation rather than a PC map scheme. With a PC map scheme, you have to have detailed unwind information for each stack frame, and you have to have a large PC map for the application. It takes up a bunch of space. And with the set jump long jump implementation and the Win32 implementation, you don't need those, or not as much of those, and you can save some space. A little bit slower at runtime in the non-exception case, maybe a little bit faster in the exception handling case. Hardware exceptions are supported there. Again, we use the mock APIs for hooking hardware exceptions. I guess I should have included a link to that in the slides here. I have a long blog post on that from way back when, what the mock APIs are like. And they're a little bit, it's a Unix-based platform, but Linux and other Unix-based platforms, when you catch hardware exceptions, you typically catch them with Signal or SIGAction. And those things are available on OS X and on iOS 32-bit, but you can't use them. Bad things happen if you try. So you have to catch exceptions with the mock APIs on those platforms, on the iOS and OS X. And again, we don't support underbar try and underbar accept. Next slide. Android 32-bit. Same detail with regard to who provides the unwind system. No, I should have said Objective-C in this one. That was copying slides a little bit. It's a C++ compiler that sets the standards. The online system is in the C++ RTL. The primary difference here is that instead of it being a set jump long jump scheme, it's the good old dwarf-based unwind info that you get from all the GCC tool chains for all the Linux platforms. It's a basic PC map scheme. Hardware exceptions are supported using SIG action. This is not a mock kernel-based operating system. It's Berkeley kernel, and they have forever used Signal and SIG action actually for telling the operating system that you want to catch various different exceptions, Control-C, access violation, and friends. And so that's how you hook the hardware exceptions on that platform. You don't need an extra thread to catch hardware exceptions on that platform. So if you had no other, if you just had a plain Pascal app without VCL or FMX, not really possible, but if you did, then you would only need one thread. And again, we don't support try and accept. Next slide. ARM 64-bit. So ARM 64-bit platforms are, again, different. In particular, iOS 64-bit platforms, they no longer use the set jump, long jump scheme, and that's all I'm going to say for right now. But it just gives you an idea that underneath the covers, there's a lot of different schemes and systems that you have to deal with to process exceptions, both language exceptions and hardware exceptions on these different platforms, and it's constantly evolving. It's a bit of a surprise to me, but that's the way it is. Next slide. Okay, so that really covers the various different platform differences on the underpinnings, and I know I didn't go into super heavy detail on those, but I really couldn't without spending an inordinate amount of time. But I would like to come back to the issue of hardware exceptions, and I talked about this before, and I've asked folks about it before, but it's a perennial issue, and since we're branching out into more platforms, I wanted to raise it for people again. So catching hardware violations is very useful, but there are two different schools of thought on it. There are purists who say you shouldn't do it ever, that it's dangerous, that an access violation may represent memory corruption, and to continue running the application in the presence of an access violation runs the risk of doing significant damage. So if you had an access violation because you had data structures corrupted and you tried to cleanly shut down the application, and that involved, persisting some data either to a database or to some other system, and you're dealing with corrupted data structures, you could do more damage than good. That's true. But in practice, the vast majority of things like access violations and floating point errors are not due to corruption. They are due to input validation failure, and most of them are null pointer exceptions. So somebody passed a null pointer to an API based on some, user interface feedback, a special case on some user interface work, or a special case maybe connecting to an external resource, and they're recoverable. They don't represent corruption in data. They just represent an oversight in code paths. And yeah, they're bugs, and they shouldn't have happened. But the pragmatic viewpoint is, well, why take down the application for something that represented that a one-time occurrence and is entirely recoverable? You can do much more damage just taking down the application. It's much more irritating to the user. Yeah, if the user gets a message box saying there was an access violation, they may get a little bit peeved, or maybe file a bug report, but at least they're not suffering data loss as a result. Then it's not desirable that applications commonly are throwing access violations, but it's nice that they don't go down in flames because of it in most cases. And that's the position that I've generally held. But there are some future issues with it. And I'll mention stack faults here as sort of a side issue. We used to support catching stack faults on Win32, and we deprecated that. This is an example of hardware exceptions that we decided were no longer reasonable to support. And we don't support them on OS 10 because you really can't, not safely at all. And on Win32 they weren't really safe either because you could catch one stack fault, and after that, if you caught another stack fault, you wouldn't catch it. Your application would just go down in flames. So it was kind of a pointless thing. So there are cases in the past where we've sort of taken a step back on some of the hardware exception handling. So the issue for the future is really there's 2 points. One is that floating point exceptions may vary from platform to platform, whether or not they're masked, whether or not you will get floating point exceptions for denormal operations, for example. Most common floating point exception that you might want to catch is divide by 0, and that's the same for integer. But how they're dispatched and under which circumstances you see floating point exceptions may vary from platform to platform. So it's kind of debatable how much we want to support that in the future, because maybe the platform won't support an exception that you thought you might catch on, say, Win32. And so maybe we want to scale back the degree to which we handle floating point exceptions. And the other issue overall is the optimizers are severely challenged. And so the issue is the compiler ordinarily protects regions around calls that can throw exceptions. So if you have a try block or stack frame which contains C++ locals, the compiler has some awareness about when you make a function call and it thinks that that thing could potentially throw an exception, and generates information to protect that region in the case an exception is thrown so that it can unwind the stack frame cleanly. But with hardware exceptions, and pretty much any memory operation can throw an exception. So from the perspective of the optimizer, that means that if it really wants to do a proper job, handling exceptions, it has to look at every single instruction as potentially throwing an exception. So you remember this function, the void mathy function, which takes 3 integers, and I showed an example where you make 3 calls to function f, which returns an object which has been constructed on a stack, and any one of those could throw an exception. Well, if any memory operation in the process of constructing those 3 objects can throw an exception, the unwind information can be really impossible to manage, especially in the presence of optimizations. So either you have to essentially disable the optimizer in order to support it, or you have to put a huge burden on the unwind information in order to faithfully unwind stack frames that have those sorts of constructs in them. So the question is going to be in the future, I think, well, how much do people really want to limit the optimizers? And I suspect that people will still want exception handling to work with hardware exceptions. But I'm raising it because the optimizer is getting better, and we've shifted over to using Clang, and as a result, we're going to have better and better optimizations, and it's going to start raising issues with exception handling and hardware exceptions. And so you may be hearing more from us on what you want supported and what you want to give up, either in the side of hardware exceptions or in the side of optimizations for these various platforms going forward. Next slide. Hey, we're done.
Great, Eli. This was awesome. There were a few questions that were more related to things like what language features are available on which platforms with the compilers, and JT put a link to the doc wiki where we have the C++ language overview and some of the older documentation about when we had C++ 0x. It had nothing to do with exception handling specifically, but I wanted to have you reiterate again about underbar try and underbar except. That's still in for the Windows-based structured exception handling, correct? But you were talking about the other compilers that accept it, but it really will start giving errors sometime in the future. Can you reiterate again what's going to happen with those, and maybe we should just stay away from them and use regular exceptions?
Yeah, they're supported on Win32 and Win64. They will work on both those platforms and will continue to work on those platforms because they were really designed for those platforms. Currently it's accepted silently by the compiler in OS 10, but that's a bug. And we will be fixing that very shortly if we haven't already. So it generates an error. And I think it probably should be an error already on iOS and Android. We're not going to support them on iOS and Android. Technically, we probably could find a means to support them on those platforms, but I don't see the value, and I don't plan on it right now.
Okay, and this was maybe a question for me, but I was sort of looking through some of the comments and so on. Is there any mechanism for querying on each platform in your own code what exceptions might be available, other than just making sure you catch all exceptions? I mean, can you know what hardware exceptions might be available on a certain platform in your own programs and adjust accordingly, or just make sure you catch everything?
No, there isn't a way for you to do that at runtime on those different platforms. That's an interesting question.
Other than the operating system documentation and any other, if you look at the chips down at Intel ARM or whatever, what might possibly be possible?
Yeah, no, the thing is underneath the covers in the runtime library, we process those exceptions and then we convert them, the ones that we do in fact catch, into typically into Delphi runtime library exceptions derived from T exception. So the user is not going to be able to query from the operating system documentation and get a clear picture of which ones we're actually going to catch. In theory, we could provide some APIs to tell you which exceptions might actually be catchable. That's something that we would put, if we put it anywhere, we would put it into the Pascal RTL. And talk to Alan and see whether or not we feel like that would be justified. I think right now it's not there, and right now the best thing is to plan on catching them all.
Absolutely. And then it's sort of, I'm looking at the slide where you talked about ARM64, and I know we're on the forefront. Apple has made their announcement that February 1st we need to make sure that we're allowing our customers to generate 32 and 64-bit iOS applications. And is there going to be any implication as far as exception handling as it relates to iOS 64-bit? I guess that's under the same heading as ARM64. Is that correct? Or?
Yeah, no, I said that it's no longer set jump, long jump based. None of these things, none of these platforms really have much of an implication to the user, except in terms of how they perform. So iOS 32-bit has a non-zero cost. It's a little bit lower performance for the non-exception case. iOS 64-bit will use PC mapped exceptions. That's a zero cost system, so it'll be a little bit more performant. So there won't be an impact to the user in terms of changing features, except possibly with respect to floating point exceptions, but I'm not sure about that yet.
Okay, and I just want to let you know, I don't know if you were probably busy, but we had a live Q&A with Bjarne Stroustrup yesterday, and one of the questions that was asked of him was what he thought some of the things that might cause, what's the right term, blockage on people's use of C++ even more in certain worlds, and you touched on it with all these different compilers that developers on different platforms, and let's not even get started on embedded systems and so on. But the questioner asked, did Bjarne think that the lack of an ABI standard as part of the C++ standard was maybe one thing that might be causing headache and blocking for C++ in now and in the future, and you covered quite a bit of that as well when you talked about different ABI efforts and different compilers doing different things, right? So even Bjarne mentioned that maybe I'm paraphrasing, that it would be good if there was a at least partial or complete, I don't know, I'm speaking for him maybe, or speaking for myself, that was defined in the C++ standards sometime in the future.
I think that would be, great. I say that now because I actually can easily we can actually easily take advantage of it from on our side, and honestly, the only player who would really have a serious issue with that would be Microsoft.
Yeah, I think, and maybe one more. I know we're running into the debug session, but we have plenty of time. Sorry. How do you think, separate from what we have to do on Windows platform with structured exception handling support, as we move to Clang compiler and our extensions across all the platforms, will that make things a little easier, better maybe for us, but also for our customers?
I think it will. We have had to jump through some hoops on some of these platforms for implementing support for things like exception handling. So in some cases, we had to do a lot of silly wrapper code because one of the platforms had GPL code in their exception handling libraries instead of, I think Apple had this at one point, instead of having a regular Apple license. So underneath the covers is a little bit more clunky for dispatching exceptions, but I don't think our users will notice it. And I think overall, as we move to the Clang code base, we'll get the advantage of a lot more people working on the libraries and the runtime and the optimizers. So overall, it's going to be a great advantage to our customers.
Thank you so much, Eli.
Sure thing.
Yeah, and everybody said this was awesome. This was an awesome talk. So